Hi, everybody. This is Rich Baranek in the ECE department at Rice University, and it's just our distinct pleasure to have Mickey Elad here from the Technion speaking in our distinguished seminar series for fall 2021. Mickey is a professor at the Technion, where he has been since 2003. Prior to that, he was a postdoc at Stanford for a couple of years and also worked in industry after receiving his PhD degree also at the Technion. He's one of the top researchers in the world in the broad area of inverse problems for signal processing, image processing, computer vision. He's done fundamental work in the space of sparse modeling, and for several years inhabited sparse land more often than the real world, and also has lately turned his sights on machine learning to great effect. He's won a number of awards. He's both a SIAM and IEEE Fellow. He's won the Imaging Science Best Paper Award, many teaching awards at the Technion, and just in a really interesting connection or link to Rice that Mickey might not know about, he has won the Herschel Rich Award for Innovation at the Technion. And Herschel Rich was a Rice alum, and there's also a Herschel Rich Award at Rice. So it's kind of a really neat, maybe someday he can come on sabbatical, visit us, and also receive the Rice Herschel Rich Award. Okay, with that, I'd like to hand over to Mickey and his talk. Thanks so much for coming.
Thank you very much. I'm delighted, and thank you for inviting me. This talk is about image denoising. It's a boring topic, or so you would think, and I'll try to convince you that there is a new life to this field. So let's start. I would suggest that if you have questions, just write them on the chat, and then we will go through them. I prefer to take them at the end. Okay. So this lecture is about image denoising. The idea is the following. You have a noisy image, and you want to clean it up. And we are designing these denoisers to achieve this goal and clean up the image. This is a very rich topic with a lot of activity, thousands and thousands of papers over the years. What I'm trying to show you today is that there is a new life to this thing, to this block of denoising. And this is quite fascinating, at least so I think. So I'll start with background. And the background is the general story of denoising, the history of this field, the revolution of deep learning. All this will be at the background. And then I'll come to the main focus of my talk, which are the three discoveries that took place in the past decade, where denoising becomes something way more than just denoising. And with this, we will summarize. Okay. So let's start with introduction and history and some definitions. When I'm saying image denoising, I'm actually referring to very specific denoising. I'm referring to removal of white additive Gaussian noise. And this is critical here. And you'll see why, because this is exactly the kind of noise I want to remove for reasons that will become clear later on. So the message is this: you get this noisy image, you are trying to clean it up, as I said before. And the assumption here is that this noisy image is in fact the sum of an original clean image and IID Gaussian noise. And this is what we are trying to do, or this is what so many people try to do. It is not trivial. This is far, far from being a trivial task. I mean, I can always filter the image aggressively to remove the noise, but then I will remove also the details. I want to preserve the details in the actual image. In fact, the way to understand how complex the problem is, what we are trying to do here is a separation. I'm trying to go back from this noisy image to the two ingredients, to the clean and the noise. Now, there are infinitely many possibilities of suggesting two images that sum to this image. Which of them makes sense? This is how tough the problem is. This is ill-posed. Why are we working on this problem? First and foremost, because it is coming up in every camera. For example, here is a photograph I took with my cell phone. Now, if it is a cell phone, it means that there is already denoising involved inside the path. I'm zooming in on these three portions, the blue, the red, and the yellow. And the zoom in shows you that the content is horribly noisy still after all this denoising that already took place. So every sensor, and especially if your illumination is poor, will suffer from noise, and you want to remove it. And this is one good reason to work on this problem. But there are other reasons. Another reason, the reason of scientists, is the idea that image denoising is in fact the front gate to our field. Anytime anyone brings a new idea to image processing, this is probably the first station to check whether your idea works for denoising. If it does, then you have a case to proceed with. So this is the simplest inverse problem, and therefore a great platform to assess all sorts of ideas. And there is a third reason. In fact, the third reason is the reason I will emphasize in my talk today. Turns out that denoiser engines, those blocks that denoise images, are doing way more than just denoising. They can serve other needs. And this is something I will emphasize in the main part of the talk. Okay. I mentioned before that I'm insisting on Gaussianity for the noise. So I'm assuming that the noise in this image is additive Gaussian and white. Why? Because it is the typical assumption, and it makes a lot of sense, especially if the noise comes from many origins, then the law of large number will take you to Gaussianity anyway. You might think that Poisson noise is actually a much better assumption. I mean, what are images? Counting of photons. So Poisson distribution seems like the proper way to go. But then again, if you think about Poisson, if the Poisson has high count, like hundreds and more photons per pixel, then you're looking at a Gaussian distribution. And if the Poisson has low counts, there is this terrific idea of Anscombe, the variance stabilizing transform, that can take the Poisson distribution image and turn it into Gaussian additive noise. So whatever you do, you end up with Gaussian noise. Another reason is the math elegance. I mean, the Gaussianity is putting a very convenient log likelihood expression, and with it you can do all sorts of things. And then if you are interested in a different noise, you can always generalize. The reasons might have stopped here, but there is another reason to use Gaussianity, and people are not aware of this reason. And here it is. Turns out, and you will see me using it again and again in the second part of my talk. Turns out that if you design an MMSE denoiser and a minimum mean squared error denoiser for specifically Gaussian noise, you are actually holding in your hands a wonderful mathematical tool with which you can do amazing things. It has to be Gaussian, it has to be MMSE. So here is another reason to think about Gaussianity. Many papers have been written over the years. This is an old extract from ISI, Web of Science, showing the number of papers that were published on denoising over the years. 2020 is not looking like this. I'm sure it is already boosted like that. Thousands and thousands of papers, and it keeps happening, keeps coming. They are coming from everywhere: China, United States, India, and many other places. Here we are in Israel. Not so many papers, but we are more influential than the usual. This is the citation, and as you can see, the citations of the papers in the US are way more influential, etc. And now let's dive into the actual denoising task and ask, how do you design a denoiser? And remember, I'm going through a sort of a background now before I'm jumping into the risky things. And I'm thinking about the classical era. And I'm asking, how can you design a denoiser? And I'm specifically thinking in terms of the knowledge we had until, 7 years ago, okay? If you would have come to one of the experts in our field 10 years ago and asked, how do you design a denoiser? Here is the answer you would have been given. You have to come up with a prior. You have to come up with an expression, mathematical expression that captures in it what good images are behaving like. Good images are tending to be smooth, so express it. Good images are supposed to be sparse under some transform, or low rank, or they should have self-similarity between regions, etc. If you can just write it down as an expression and augment it in a Bayesian approach, you are looking at an optimization problem that can take you all the way to denoising. And it will typically look like this, typically. Basically, this expression says, you give me Y, the noisy image. I'll try to figure out who is X, the clean image. X should not be far away from Y. This is one requirement. This is exactly the log likelihood of the Gaussianity assumption. And then again, X, you know, if you had only the blue part, then X is Y and well done. X now has to behave well. Row of X says X. You cannot be anything you want. You have to be smooth, you have to be sparse, you have to be something that aligns with what we expect images to behave like. And then you can minimize this in iterative methods or find a direct method to apply something that is in the spirit of what you see here, and you end up with X hat, your denoised result. And if you look at the literature, what you see is an evolution of ideas all around this expression, where row of X keeps changing. It started with L2, then it went to robust statistics, wavelet came in, partial differential equations. As I told you, every field that came to image processing found itself serving denoising as part of the entry test to the field. Sparsity method, self-similarity, low rank, etc. And this history stops at around 2013, and that's it. Nobody proceeds to work on it anymore, at least not this way. This is the classical part of our history. At some point, already in 2010, I think, people in our field started believing that we are touching the ceiling in terms of denoising. Here is a paper that says, is denoising dead? This is a paper by a good friend of mine, Peyman Milan, found with his student. And what they try to do is to come up with a bound that says, what is the truly best you can get in denoising? Are we touching the ceiling? A similar situation is being discussed in this paper by Anat Levin and Boaz Nadler at the time from Weizmann Institute. Again, devising a bound for the best performing denoiser in order to know whether we are touching the ceiling. And why did we feel that this is the case? Because many different algorithms started getting very similar results, and improvement was almost impossible. And yes, this was the feeling 2010, 2014. My students, when they came to me and said, listen, let's do something about image denoising, I said, no point. There is no point because you will be working hard to get hardly any improvement over existing work. And this was a horrible mistake because it turns out that there is new life to denoising, a new life which we were not aware of. And this new life has to do a lot with the presentation, the coming of deep learning to our field. But it's more than just yet another way of designing denoisers. The new field of denoising is very much alive and kicking because of several excellent reasons. And all of them has to do with deep learning in a way. First of all, with deep learning denoising, you can adapt your denoiser to the image. So you have a good performing denoiser, and now a bizarre and exceptional image comes in and wants to be served. You don't have to serve it using the denoiser. You can actually tweak it in order to do better for that image. Nothing that happened before. You can think beyond pick a scenario. Don't think MSE, think SSIM, think other measures of goodness. You don't have to design your denoiser in the classical way. You can adopt different ideas like GAN-based. Suddenly we can then ask questions like, what about realistic noise? You know, if you have a camera, the noise is not truly Gaussian. So why insist on Gaussianity? What do you do about the actual noise in the camera? You know, in the classical path, we couldn't do anything about it. Now, in this era, we can. So all these questions suddenly get answered. And yet, and yes, above all this, denoisers, and this is what I will emphasize, turns out that denoisers that are designed either by deep learning or the classical approach can be leveraged in more than the usual cleaning up of noise. And all of this brought new life to this field. Let's talk briefly about the deep learning revolution. Remember I asked before, how do you design a denoiser? And I gave you the answer of the classic approach. Now let's give the answer that started in 2012 up to now. This will be the method of choice for anyone who does denoising today. And it goes like this. Gather a large data set of clean images. Call them XK and have capital N of them. Add Gaussian noise to them, the noise you are trying to serve. So add white additive Gaussian noise, and now you have many, many pairs of clean and noisy images. Define your denoiser as a machine that has parameters theta, some sort of a network that will take you from the image Y all the way to the image X hat. And now, this is the block diagram that describes what I've just described. You take the X's, you add the noise, you get the noisy images, you push them through this parametric system, and you hope to get terrific looking images that will be as close as possible to what? To these images. So define your loss. It doesn't have to be L2, but L2 seems like a natural way to go. And design your parameters, theta, of the denoiser. You basically are designing a denoiser. Figure out your theta parameters such that you do the best in terms of this loss. Right, a new way of designing denoisers. So all these old methods that assumed piecewise movement, self-similarity, sparse representation, scale invariance, whatever you had, GMMs that were so effective, all of this is lost, and we have replaced all of them with what? Supervised training over a large data set. And all of these are sort of obsolete. 40 years of activity, 20 years that I spent working on sparse representation, and nothing in this domain is of any relevance anymore, because you can design amazingly performing denoisers with this approach, the supervised learning approach. And a new evolution starts. The revolution that started in 2012 with a little bit of denoising, little bit of daring by Berger and al, and others that followed. There were several years of confusion. Nobody touched this topic, and suddenly it burst. And if you go to NeurIPS, to ICML, to CVPR, to ICCV, you'll see many, dozens and dozens of papers on denoising, all of them adopting this new paradigm and tweaking it in all sorts of interesting ways. So a new life came to image denoising just because of deep learning, but this is not the life I'm referring to. This is just sort of, okay, you can do better with denoising, but we can actually do so much more. I'll say something very brief about this, just to let you know that the classic methods are not dead. They are there and they will be used. And there is some sort of synergy between the classics and deep learning. And I'll say very briefly the story. The message is this. This is what we do in the new era. We gather training set. We define an architecture for the denoiser. We define a cost function and we optimize, we train. Defining the architecture, we have no clue what to do about it. We just guess. If you look at what people do in order to come up with architectures for deep learning, for whatever problem they are serving, they will do one of several things. They will either copy an existing network, typically UNet, VGG, portions of them, or they will pile the goodies that are creating neural networks, convolutions, fully connected layers, batch norms, pooling, stride, skips, scale up, scale down, etc. Or there is another trend of NAS. NAS says, you know what, let's optimize not only the parameters of the network, let's optimize also the architecture itself. And all of this are not even coming close to nailing the proper architecture that should serve a specific problem. What is the alternative? Just before talking about the alternative, just a glimpse at 2019 papers from CVPR and MIPS, and you see again and again, either copying a network or building a network by piling elements without any justification. Many parameters, I'm talking millions of parameters in each of those networks, and this is the typical trend. This is what people do in order to denoise. Again, what is the alternative? The alternative is to go back to the classics. Take an existing algorithm that has some origins, it knows what it does, unfold it into chain of operations, and now think about this as a network and forget about the classics, now train it supervised. If you do that, you benefit from both worlds. And you will benefit in many, many ways. For example, you will get way more concise networks that has less parameters, and therefore they are training on smaller data sets. They can adapt better, they can perform better on data sets. They have perfect explainability. If you take, for example, this is something we did. We took the KZD denoising, something we invented in 2006, unfolded it, and then trained it. Everything in this network is understood. If it is an activation level, we know exactly what it means. If it is a parameter, we know exactly what it means. And that means that we can leverage this network and do something else with it. And this is a line of thinking that we have been developing in my group in the past several years, but this is not the main thing we do. Okay, and now let's come to the focus of my talk today, recent discoveries. And what I'll try to do today is to show you that this innocent looking block, the denoiser, can do other things. It can solve Windows problems. And this is something that started in 2013 and it is still very vivid until today. It can be used for synthesizing images out of thin air, and this is quite recent. And it can be used in order to ask more daring questions about denoising itself and other inverse problems. How do you recover high perceptual quality results in inverse problems? And what I'll do now is to dive into each of those three and tell you the story as it took place. Okay, so let's start by inverse problems. Denoising is an inverse problem. You give me this noisy image, and I'm supposed to recover the clean image. Deblurring is an inverse problem, where the image is assumed to be blurred and noisy, and I'm trying to recover the original. If you give me an image with missing pixels, and I'm trying to revive those missing pixels, exactly what happened here, it's an inverse problem. The same goes for those missing values in the demosaicing, where instead of giving me R, G, and B per each pixel, you give me only one value, and I'm supposed to guess the other two. Tomographic reconstruction, where you get projections, the sinogram, and you're trying to recover the intersection. Or super resolution, where you give me a smaller image, and I'm trying to scale it up and get high resolution image that looks vivid, crisp. All these are inverse problems, and all of them can be formulated in the following equation that says there was an ideal image X. It went through a known operator H. I'm assuming that H is known to me. There is an operator H, a linear one, that multiplied X. Then there is additive noise. It doesn't have to be Gaussian this time, but let's just assume it's Gaussian for simplicity. And you get measurements. Those measurements could be the noisy image, the sinogram, or whatever. And you're trying to figure out from Y and from the knowledge of X, from the knowledge of H, what is X? These are the inverse problems we're looking at. And here is my question now. How do you solve inverse problems? Well, again, we have a fork between two options. There is the classic approach, and there is the more modern approach. And I'll talk about the classic approach. And it looks like I'm going backwards, but actually, you'll see I'm closing the gap with the most advanced methods in no time. So let's talk about the classic Bayesian approach. Again, come up with a prior and form an optimization problem, just like before, very similar to what we did. This is the only difference. This expression basically speaks to us. It says, I'm searching for X, such that if I degrade it using the same operator H, it should be not far away from 1. This is the log likelihood under the assumption of Gaussianity. And then again, X, you should be well behaved. Okay, and you optimize this. This is the map estimation. This is an extension of what we did a minute ago for denoising. You will be iterating or suggesting other alternatives in order to solve something or approximate it. And it works great. And you might wonder, why am I not showing you the more advanced neural network-based supervised learning alternatives? Yes, they exist, and yes, they work great. But I have a reason to show you this, because you will see that in a terrific turns of events, we can jump from this breed of classical method all the way to the most advanced method. Oh, another question. Suppose that someone gave you a denoiser, a good performing denoiser. Can you solve an inverse problem with it? Surprisingly, the answer is yes. And this came in this beautiful paper by, I'm having difficulty with this name, Venkatakrishnan, Charlie Bauman, and Brent Wahlberg. A paper that they published in a conference in 2013, and the paper was amazingly beautiful. And what they proposed is something called the plug-and-play problem. Several years later, and inspired by this work, we came with our own extension of it. We called it regularization by denoising. It's a different scheme, but in the same spirit. And both papers, and there are many follow-ups to them, both papers basically suggest that your denoiser should be used as a regularization. How exactly? You will see in a minute. And if you look at the bottom line of those algorithms, here is what you will see. You'll see an algorithm that keeps jumping between simple operation and a denoising, simple operation and denoising. And of course, it has to be well designed. If you do so smartly, you start with Y, the degraded measurements, and you end up with X hat, your desired solution for the inverse problem. How does it work? Let's have a look at the plug and play. And I'm giving you the nutshell version of it. Remember, this is what we are after. And let's just assume that I have all the ingredients in place. I know the prior, and I have the operator H, and I have the measurements Y, and I'm trying to figure out the minimization for this in order to get X hat. And then I'm doing something quite dumb, and I'm coming up with a variable V that is supposed to be exactly equal to X. So that basically this expression remains expressed with respect to X, but this expression is now a function of V. Nothing really happened. And now I will turn this constraint into a penalty. This is not what the paper did. The original paper of the plug and play used something far smarter, which is the augmented Lagrange, but I'm trying to simplify things for you. So let's just assume that I'm penalizing for the proximity between the two. Okay, now comes the bottom line. I'm trying to minimize this with respect to both x and v. Let's just jump between one while freezing the other. So I will minimize this with respect to x while freezing v. So this expression drops out and we get the first and the third. And so it's a quadratic expression, very easy to handle. It's a linear system. So yes, this is the simple part that I mentioned in those block diagrams. And then you freeze x and you optimize with respect to v. So this now falls out and you get this expression and this expression. You look at this and you say, my God, this is the denoiser. So instead of doing this, let's apply a denoiser. And now something terrific happened. You don't really have to tell me who is rho of v, what is your pile. Just tell me who is your denoiser. And this is the plug and play in a nutshell. So you keep jumping between solution of this quadratic expression and application of your favorite denoiser, and hopefully things will go well. This is the plug and play. Here is the red option that we developed several years later. Red regularization by denoising starts from the very same place, this expression. But instead of doing this split of variables, what we do is to suggest a very specific expression for rho. We are suggesting this expression that has the denoiser inside. So we have an explicit expression for the pile. And why this expression makes sense? Let me just give you a sort of intuition. You know, you can always think of a denoiser as a sort of a smart smoother. So instead of writing x minus d of x, let's write x minus s times x, where s is the operator that does the smoothing. This is a spatially varying and spatially adaptive smoothing, very smart smoothing, because your denoiser knows what it does in every place in the image. And if you look at this, what is it? It's a Laplacian smoothing, because identity minus smoothing is exactly a Laplacian operation. So yes, looks great, terrific. So then our message is, if you minimize this, if you get a value, or if you get x such that the value of this is small, you're likely to look at a good-looking image. But we have nothing. We have nothing, because if I'm trying now to minimize this expression with respect to x, I find a need to take a derivative of the denoiser. Now, if the denoiser works on an image of size 1000 by 1000 pixels, it means that it starts with 1 million pixels and ends with 1 million pixels. So the derivative is a matrix of size 1 million by 1 million. This is the Jacobian. Are you seriously going to complete the Jacobian? Then a small or not so small miracle happens. Turns out, under some conditions on the denoiser here, by the way, if it is MMSE for Gaussian noise, these are the conditions, or at least reflection of them, then the derivative of this expression is nothing but the residual of the denoising itself. You don't have to take any derivative. You just have to apply the denoising itself. Okay, so armed with this, if I take a derivative of the whole expression, I can do, for example, steepest descent. It's not the only option, but there are a bunch of options. And what do you see here? A bunch of simple operations in application of a denoising in every iteration, just like in plug and play, but in a different flavor. And yes, it works. By the way, if your denoiser is MMSE, then something amazing happened. This whole expression is known to be convex. And if it is convex, it means that whatever you do here, you will get to the global minima, another benefit. Okay, does it work? Let me show you some results. Oh, this is a ground truth image. This is degraded image by blur, horrible blur and some noise. And what you see here let's start here. This is the NCSR, a very specifically tailored method for deblurring and for super resolution, NCSR, and it works beautifully. And this is the result we get. What you see here and here and here are all the results of plug and play and red. Let's start with this. This is red deploying as a denoiser the median filter, the dumbest denoising you can ever think of. It is not MMSE denoising of any sort. You just plug it, run the algorithm, and you get quite nice restoration. Not as good as this, but quite reasonable. And for what? For ingredients that are so simple. But you see here, plug and play in red applied with a very specific denoiser called TNRD, a better denoiser based on neural net. One of that was invented by Prof in 2017, and it performs even better than NCSR. I'm guessing that if we deploy today's denoisers, we will get even way better results than NCSR. So you can actually take the most advanced denoisers from deep learning and apply them within their scheme, and then you solve general inverse problems. This is a similar situation for scaling up an image by a factor of 3, if I'm not mistaken. This is by cubic interpolation NCSR, this specifically tailored method by Dong. And this is the TNRD and RED that perform better. And again, they are relying on a very specific denoiser. So this was the first part. Those two papers that I mentioned, those two, by the way, those two extracts that you see here from 2013 and 17, they were taken several weeks ago, so the numbers are bigger. There are a lot of citations to these two papers, and there are a lot of follow-ups. Why? Because the idea is fascinating. You have a denoiser, and you can use it in order to solve other inverse problems. If you look at the follow-up papers, you will see that many of them are trying to struggle with convergence analysis of those two algorithms. What are the conditions on the denoiser to guarantee that the algorithm is well behaved? How to deploy them in other applications, or creation of other ingredient of variants of those algorithms, and those exist as well. So there are a lot of follow-ups. One follow-up that I'm truly excited about, and this is closing the circle with what I mentioned at the beginning, is the following. If you have this algorithm now, you can unfold it, and you can train it end-to-end in a supervised way. You have an architecture that emerges from plug and play or from RED. The architecture is well motivated, and you can now train it end-to-end, or train the denoiser that repeats itself 5, 10 times in order to do the best for a family of inverse problems. So you jump straight to the forefront of solving inverse problems using supervised learning techniques. This was the first chapter that I wanted to cover. Let's move now to synthesis of images, something entirely different. I don't know why, but suddenly in the past 5 or 7 years, there is a lot of interest in synthesizing images out of thin air, generating images by a software. Typically, it comes hand in hand with another notion of networks called GANs, generative adversarial networks. I'm sure you've heard about these. Those are the networks that are built of 2 portions. There is a generator that starts with a random vector and ends with an image. And there is another network that is criticizing the first network. It's a classifier that tries to tell apart synthesized images versus true ones, and they fight each other. It's a game between 2 networks, and they keep improving themselves up to the point where the classifier cannot tell anymore synthesized from real images, and then you have a great generator. And it works. Those images, they were never photographed by a camera. Those are synthesized by a machine, by a network. These faces are of people that never existed. In fact, they are taken from a webpage called thispersondoesnotexist.com. You just go to the webpage and refresh the page, and it keeps getting new faces of synthesized people. Now, you might wonder, why are we so fascinated about this idea of synthesizing images? First of all, I think it is fascinating by itself. I don't need any excuse. But if you are searching for other reasons, I would say the following. If you have a network that can synthesize images, you have access to the ultimate prior for inverse problems, the ultimate prior for image processing. This is the holy grail of image processing, holding something that knows so much about the distribution of images. This is what those networks give you as a side benefit to what they do. And therefore, they can be used in all sorts of ways in order to solve problems, to compress images better, to solve inverse problems, etc. Now, my question is this: can we synthesize images differently? Let's be more specific. Suppose that I've given you a denoiser. Should give you a deja vu. This question has appeared before. Suppose I'm giving you a good-looking denoiser. Can you synthesize images with it? Surprisingly, the answer is yes. And those are the papers by Song and Ermon from the past 2 years. This is a group that sits in Stanford University and doing brilliant work. This is a paper by Katkoda and Simoncelli, a terrific paper that, honestly, this was the paper that started my inspiration about this topic. They are sitting in NYU. And what they are saying basically is, yes, you can use a denoiser as a projection to the manifold of images. It's not heuristic. I'll show you in a minute. It's actually pure mathematical result that can take you all the way to synthesis of images. And again, if you dive down into the actual algorithm that they are proposing, you will see something very similar to what we've seen before. Simple operation and denoising, simple operation and denoising. Yes, there are differences, of course. The operation will be different. The denoising is applied with different levels of noise for reasons that will be clear in a minute. But this is the structure of those algorithms. And yes, they start from noise and they end up with a synthesized image that look faithful. Those images you have seen before. How does it work? Let me give you the nutshell story here. Suppose that you don't, but suppose that you have access to the probability density function of images, P of X. Suppose that God gave you access to this function and now you are interested in sampling examples from it in order to create images that are random drawing from this distribution. How do you do it? Here is an idea. You start with a random noise, just arbitrary vector, and you apply iterations of this sort. What are we looking at here? Instead of working with P of X, I'm working with log P of X. It doesn't matter because log is a monotonic function. If you increase the log of the probability, you increase the probability. And so if I go up the gradient, I'm doing steepest ascent, and I'm creating a new image from the previous image that is slightly more likely to exist. So I'm basically climbing the distribution function. If you do this many times, you get stuck. You get stuck and you get nowhere because you will fall into local maxima and nothing happens. Then comes this Langevin idea that says, no, apply these iterations, but keep injecting noise. And A and B, they are not free to go. You have to choose them very smartly. And Langevin gave us a formula for exactly what should be done here in order to get proper behavior. And then he proves that if you do this, you guaranteed to sample from the distribution. If you do this infinitely many times, your X infinity will be a valid sample from the distribution. Wonderful. Wonderful, but meaningless, because where on earth will you get access to this horrible looking function? This horrible looking function has a name. It's called the score function. And people in statistics are familiar with it for many, many years. And as it turns out, remember, we have miracles in this lecture. So here's another miracle. As it turns out, you can approximate this score function using what? Using the residual of the denoiser. So you bring a denoiser, not any denoiser, it has to be MMSE denoising, MMSE referring to Gaussian noise. And if you apply it and you compute just the image xk minus its denoising result, you will be looking at an approximation of this expression, which basically I'm telling you that when you have a denoiser, you have access to something, not exactly, but something that has to do with the prior. They keep talking with each other. And again, what are we looking at? Now that we know that this is the replacement for this expression, you have an algorithm that does simple things and call denoising again and again, and you get samples from the distribution. Terrific. Actually, the things are a little bit more complex. Because if you run the algorithm that I've just described, it will actually take you forever to converge. And why? Because this is P of X, the probability of images. Suppose that we are talking about images of size 1 million pixels. The space of R1 million is essentially empty. In most of this space, probability of X is simply 0. So if you put me in some point there and trying to pull me towards the gradient themselves are 0. So nothing pulls me towards the manifold of images. So I need some sort of a slope to pull me, some sort of magnet to take me into the manifold. And the magnet is the Unveil-Langevin algorithm. And the Unveil-Langevin algorithm says, let's not work with P of X. Let's work with blurred version of it. And luckily for us, blurring of distributions is very easy. All you have to do is to add Gaussian noise. Now I'm adding a synthetic noise. So basically, I'm starting not by sampling from P of X, but sampling from P of X plus some V with very strong noise and slowly decay this noise. So I have something that pulls me in, and eventually I will fall into this narrow manifold as I wanted. This is the Unveil-Langevin algorithm. Okay? So again, the core idea, start by drawing from the wider distribution and slowly change the distribution as you run inwards towards the manifold. And it works. Those are the results from Katkoda and Simoncelli, starting from random and ending with an image. or starting with random and ending with an image of faces or object. This is from Song and Elmo. You might wonder, how come they get these images and Song gets faces? It's your denoiser. It's all about your denoiser. If your denoiser has been trained to handle faces, it will produce faces. And if you are thinking, well, it doesn't look so convincing and it doesn't look so great, let me show you something else. This is a paper that was published a few months ago. And basically the message in this paper is diffusion models. This is exactly those methods, the Elad. Diffusion models beat GANs. Basically, the claim today is the best performing synthesizers for images are those animals that do the Elad in denoising. And just to illustrate, those are the results of one of the best performing GANs. It's called a BGAN. FID is a measure of goodness of those images, how faithful they are to the distribution of images. And what you see is that the FID is improved dramatically in the diffusion methods. They are more diverse. So it really works. And what are we looking at? An innocent looking denoiser, MMSE denoiser for Gaussian noise suddenly synthesizes images out of thin air and beats all those GANs. I'm talking about thousands of papers that were published in the past 5 years, improving GANs again and again and again. And suddenly a sleazy denoiser can bypass them so easily. It's fascinating. And this brings me to the third topic, which will be building on the second. Targeting perceptual quality. The story is slightly different and quite fascinating. I'm giving you this noisy image, and I'm asking you, clean it up for me, please denoise it. And you will go and apply your best denoiser, and you will get this result. And at first glance at this image, you will say to yourself, wow, this is terrific, this is wonderful. But then again, if you look at the original image, there is a difference. There is a difference. And it's not about the difference in details. I'm talking about the fact that this image is sharp and this image seems to be a bit blurred. Why is it blurred? Turns out that we can explain this blurriness quite clearly. Here it is. If this is the manifold of the images where every point in this curve of this manifold is a valid image to have, and you give me a noisy image, so you threw me away from the manifold, I'm trying to make my way back. And the question I'm asking basically is, who could be the explanation in this manifold to me, the noisy image? And I'm looking and discovering that all of these are, at some point, explanations, valid explanation. Now I'm doing MMSE denoising. You know what MMSE denoising does? MMSE denoising is the conditional expectation. It's an average of all of these images. You will be averaging all these images to give me the best result, which will have necessarily fall again outside of the manifold. So can we do something different? Can we actually handle image denoising, but insist on getting crisp, sharp-looking results? So basically, instead of getting a specific image here that will be the average of all those, I would like to get samples from the posterior. This is what I'm going to. Okay. So here is the question. How can we denoise an image while targeting high perceptual quality results? And here are the answers that we gave in 2 papers that came from my group just recently. This paper will appear in a workshop in ICCV. This paper in the same workshop, I think. Yes, so both of them will appear in the same workshop. And the message in both papers is, yes, you can sample from the posterior distribution. Don't take expectation, sample from the posterior. The first paper does it using conditional GAN. This is a paper by Guy Ochayon, Theo Adrai, two of my students, Grisha Waxman, who is a PhD student of mine, and Pema Linfar, who collaborated with us. So conditional GAN. And the second paper took an entirely different approach of Langevin method, basically MMSE denoisers iterated in order to get this solution. A paper by a student called Bahjat Kawar and Grisha Waxman as well. One thing amazing that happens here is that you are no longer looking at a single solution. If I'm sampling from the posterior, I will get multitude of solutions. I will show you a bunch of images that could explain your outcome. All of them have to be lovely to look at, sharp, crisp, and might be different from each other. Okay, so let's zoom in into those 2 papers, and I'll start with the second one, the stochastic image denoiser that uses Langevin. What we are after is drawing from the posterior, P of X given Y. And it should be very similar to what we did in the synthesis. Instead of working with P of X, we work with P of X given Y. So here it is. This is Langevin with conditional score. the score condition on y, because well, we got y, so let's just use it. And if I do that, I will be getting a valid image from the distribution P of x that would explain y. Let's use the base rule. Replace the order between these two. Very simple. You get this. Now, this would have been the frightening part. Sorry, please excuse me. This will be the frightening part, but it is no longer the case. It is a residual of a denoiser. We know exactly what to do about it, and we are left with this part, which looks so easy. It's the probability of y given xk. You know, it looks like the log likelihood, and we know everything about the log likelihood, right? So it looks innocent, and the question is, what do we do with it? And here comes the complication. We are using the Langevin method in the annealed version, which means that there are two noises involved. In fact, three. There is the measurements noise, the noise in the image itself. There is the synthetic annealing noise that we inject in order to widen the distribution, remember? And there is a third noise, which I don't even bother to mention, which is the random noise we inject in every iteration. Forget about the third. What is the relation between these two? If you disregard this question, you get stuck. So we had to think about it quite hard, and we eventually decided that the way to go is to assume that this noise is actually residing inside N. It is a portion of the noise in N. And that means that we are basically peeling the noise from the image. We start from the noisy image and we peel noise again and again and again up to the point where it becomes clear. And then if you do this, this expression gets a clear expression. This conditional, grad of the conditional becomes very simple, and we know what to do about it. And now plugging it, we play with these equations, and let me show you what it does. If these are three noisy images and we apply the algorithm, it keeps peeling the noise from the images, and we end up with clean images that are sharp and crisp. Again, I have to emphasize what we do here is to call an MMSE denoiser again and again and again in order to get a denoising result of a different flavor. Okay, what you see here is the example I started with: ideal image, noisy image, MMSE, 3 samples. The amazing thing about these 3 samples is that if you take them and subtract from the noisy image, you get a residual that is behaving just like ILD Gaussian noise. So they are all valid. So which is the proper person? These are 3 different people. Who of them is sitting in this image? You will never know. This image went through 3 levels of noise: low, medium, and high. This is the MSE denoising. You see something quite expected. As the noise gets stronger and stronger, the blurriness is emphasized. Why? Because you are further from the manifold, you aggregate more images. And so you lose details in the skies, you lose details in the tower. These are samples corresponding to each, and all of them look comparable because you just sample. They are different from each other, of course. 4 noisy images, and per each 4 samples. And you sample and you get slightly different people because this is what you have here. You will never know. This is giving you an option to talk about the uncertainty inside your solution, something that we keep forgetting about. When I show you the MMSE solution, you never think, maybe it's not this person, maybe it's a different person. No, but now you are aware of the differences that can exist for different people. Last example, clean images, noisy images, MMSE, and our result. And as you can see, our results are just sharper and more vivid. Okay. This was the first approach. Now let's move to the conditional GAN approach. I'll step back to the very beginning. You have a noisy image. You want to design a denoiser. This will be the output. You want the output to be not far away from the ideal image, so come up with a loss function that says the two should be close by. But then comes the desire to force the image to look great, to look competitive to the ideal image in terms of its sharpness. So what do? The typical thing to do, and people have done it in all sorts of contexts, is to add a perceptual adversarial loss. The message is the following: take your denoised result, take your clean image, and fit them to a classifier that tries to tell them apart. This classifier gets an image and is supposed to say, oh, this is an output of a denoiser. No, this is an ideal image. If it is able to tell them apart, it means that your denoising is challenged. And so this will be exactly this loss. And you will do minimization of this, and yes, your images will become slightly more sharp. But this is not what we are after. Why? Because there is a compromise between these two forces, and they are contradicting each other. There is an amazing paper that I recommend that you read, a paper by Yochai Blau and Tomer Michaeli, published in 2017. I'm proud to say that it came from my university, Technion, where Tomer Michaeli is a faculty. And this is a theoretical paper that shows you, proves you, that perception and distortion are at odds with each other. They are contradicting. It should remind you very much of the interplay between rate and distortion in information theory. Let's explain this graph. Distortion is what you think of, MSE or whatever distortion. You want to be here. You want to have the smallest possible distortion, as much as possible in this problem. Perception is how good looking your result is. And the lower, the better. If you are here in the bottom, the result you get is perfect looking. You want to be in this origin. And if not, you want to be in this region. They tell you, Yochai Blau and Tomer Michaeli, it's impossible to be here. Any algorithm that will do restoration must sit above this curve. There is a curve, it has to be convex, and it defines the ultimate performance. This curve has two interesting endpoints. This point is actually quite familiar to us. This point is the MMSE denoising. It basically says, I don't care about perceptual quality. Don't mess with me about perceptual quality. Just give me the best possible distortion, and I'm getting this. And of course, I'm paying in perceptual quality, and the result is blurred. The other point is a point that nobody is referring to. This is the other extreme where you say, I'm willing to sacrifice distortion, but I really need the image to look as great as possible. So make it as great as possible, but make the distortion the smallest you can. And what they have proven is that you have to pay exactly 3 dB in migrating from this point to this point. So we are after this point. What I've shown you in the previous slide is sitting somewhere either on the curve or above the curve. How do I get to this point? Getting to this point is exactly the sampling from the posterior. I'm trying to sample from the posterior exactly as I've shown you with the previous method. Now let's do it with the posterior sampling based on a conditional gun. And just to illustrate that it works, these are the results. If this is an image and this is a noisy version of it, these are samples from the posterior obtained with our method, the posterior sampling conditional gun. How does it work? In a nutshell, it looks like this. We have a denoiser. It's no longer a regular denoiser, it's a randomized denoiser. Why? Because it will be sampling. So it has an additional random vector noise, Z, that whenever it changes the output. And for any denoising that you apply, if you play with this vector, you keep getting different outputs, all of them valid denoising results. Okay, lovely. Now you have a critic. Our critic will get pairs of noisy and denoised or noisy and clean images, and it will have to tell them apart. Why are we messing with a noisy image? You see, if I would have done what I've done before, showing you the denoised and the original, then the critic is only struggling to understand whether your result is good looking or not. What I want the critic to say is something even more profound. I want it to say, this is a good looking image, and it is a valid denoising result for your noise image. So it makes sense to be a solution to your denoising task. So this is why we are feeding the noisy image. And it looks easy, but now the missing part, and this is critical, is the loss function. How do you train this? I've shown you a loss function before, and I claim that it doesn't work. So how do we bypass this trade-off between distortion and perception? So here's what we did. This is the regular loss for conditional guns. Don't be alarmed. It's much simpler than you think. Or I will try to explain it as much. So I remind you, we have two ingredients, denoising with parameters theta and critic with parameter omega. Okay. So this expression says the following. Let's freeze the denoising. Now let's update the critic. And the critic tries to make sense to differentiate between pairs of clean and noisy images versus denoised and noisy image. And so it will try to maximize this expression, making this much bigger than this. And if it is indeed much bigger, it means that the classifier can tell apart denoised versus clean. Then comes the denoiser. I'm freezing omega. and I'm trying to minimize this expression, basically magnify this expression, so the denoiser tries to close the gap again, basically confuse the critic. And so this is the struggle. And all of this is lovely and meaningless. Why? Because for this to work well, you have to have many, many examples of pairs x and y's. You have to have many x's per each y and many y's per each x. Many y's per each x is very easy. You have a clean image, give me many realizations of noise to add to y. This is easy. But getting y and creating many x's to it, how do you get it? You will never be able to do it. So we have unbalanced training set, and so we cannot minimize this. So we are stuck unless we bring in an extra force that will help us. The extra force that comes to mind is this that says, you know what? Yes, don't forget, your denoiser is supposed to be a denoiser, so whatever it produces should be not far away from the clean image. But this would be the wrong way to go. If you do that, you go away from this point dimension, because this is exactly the distortion. I don't want to mess with the distortion. So what do we do? This is what we did. We said the denoiser itself, the one output, I don't care what it is. But if I take average over many, many realizations of the random noise Z and average them, I'm supposed to get the MMSE denoising. And this should be close to X. And if I do this as a loss function, then I'm avoiding this pitfall of mixing distortion and perception. And this is what we did. And we get MMSE free. What you see here are just results of this algorithm with growing levels of noise, original, noisy, conditional GAN, the results we get, and the DNCNN. DNCNN is a terrific denoiser by Zhang and his students that was published in 2017, I think, or 18. And it's our MMSE. And zooming in, you will see that our results are much sharper and crisper compared to the MMSE that necessarily averages things. And the paper has a lot of additional things. I think I'm short in time, so I'm going to skip this part, and I'll show you only the essence of it. And the essence of it is the following. Why am I doing denoising alone? I can actually serve any inverse problem now and sample from the posterior. Let's do this. And this is exactly this paper by Jat, a follow-up to his previous paper. This is a paper that will appear in NeurIPS 2021. And the message is, let's sample from the, I'm going to skip all those equations. We are sampling from the posterior, but now with the degradation involved. And look what we get. This is ideal images. This is observed images. We have the upper part noisy and the bottom part missing. And we run the algorithm as emerges from our equation with Langevin dynamics. And this is what we get, 2 samples. And of course, we have a lot of freedom in the bottom part of the face. And indeed, it is practiced by the algorithm. And of course, in the upper part, it just denoises and has way less freedom. So this is impinging. This is super resolution. So we are trying to go back from these images to these original images. Those are the samples we get. These are their average, which is the MMSE. And this is their standard deviation. So we have a way of quantifying the uncertainty in each pixel. Similar, we work on bedrooms and we have degraded images, loss of resolution, samples, and the samples are slightly different. If you dive a little bit into the images, you will see that they are slightly different. And this is their mean. This is blur and noise. So the image is heavily blurred and noisy, and we are trying to recover. Those are the samples. And these are the mean and the standard deviation again. So things seem to work very well. And compressed sensing. Compressed sensing, you are supposed to be familiar with it. The idea is the following. Let's just imagine that those images are of size, say 100 by 100 pixels, so 10,000 pixels. So I'm projecting randomly onto 1250, this is this number, vectors and giving you the numbers, and I'm trying to figure out, okay, what was your image? Disregard this. This is back projection. Of course, it doesn't supposed to work. And these are the samples we get. Look, we have a lot of freedom. Losing factor 8 in compressed sensing gives you a lot of freedom in producing the image that could explain the measurements. And this is the average. This is the MMSE. Okay? Or here's another example, the same face, 3 levels of compression, compressed sensing, factor 4, factor 8, factor 16, and a single sample in the MSE. the MMSE and the standard deviation. And of course, the standard deviation will be much more pronounced as you go to less information, because then the uncertainties in your recovery are bigger. This is where I stop. I just want to remind you that there are plenty of things to be done in this field, because there are shortcomings to the algorithms I've shown you. The Langevin method is still slow, even with the annealing option. It is limited to specific families of images. I don't know if you noticed, but I worked on faces, on bedrooms. I'm not working on general content images, and for a reason, the denoisers are not there yet. And in the last part, I didn't show you, but we are relying on SVD of age, the operator age, in order to survive this task. So it's a cumbersome step. So just to summarize, denoising is not what you think anymore. It is so much more. It has so many opportunities and challenges in designing denoisers and using them to serve other needs. And suddenly new doors open, new horizons open. And this is why I'm fascinated about this. Now, in 2016, I resisted deep learning. Honestly, I was among the people who said, I will never touch deep learning. I'm no longer there. Everything I do today is heavily influenced by deep learning. In this talk, even if I didn't mention deep learning, it is there looking at us from every slide. Everything that I've shown you relies on deep learning to exist. So deep learning is not necessarily the bad guy in the neighborhood. It could be the good guy if it is deployed smartly. And this is where I stop. Thank you very much.
Beautiful. Really interesting talk. And let Cesar, are you still here?
Yeah, I'm still here.
Okay, great. So I think that we can have folks can put questions into the chat, right? But we can also.
Give people the option to talk.
Yeah, exactly, and it's best if people can talk, but then it could be that you need to like promote them to have the ability to talk.
Yeah, so if there is pressing questions, they can send a message to me on the chat, and then I can allow them to talk. Yeah.
Okay.
They can raise hands. I think if you look at the list, you see a raising of hands.
Yes, correct. So
I raised my hand. So maybe I'll start with a question to get while people get kind of rolling. This is fascinating, Mickey. And I think the thing that is so interesting is that it's not only like useful, like practically useful methods for denoising or synthesizing images, but it also sheds light on so much on how these methods work. So I think this is really, really interesting. Here's my question, and it actually has to do with something you talked about at the beginning of the talk, and this point number 2 here. And that is how you talked about how deep learning is like prominent in this approach. Looking at it in the other direction, does anything in this approach shed new light onto why deep learning, works so well in these kinds of applications? Does that question make sense to you? And if so, what are your thoughts?
We don't know. We do know that deep learning denoisers are performing better, and therefore they are closer to MMSE, but they are not there yet, which is why, for example, when we take a general purpose denoiser, it doesn't produce good looking images, and we are still struggling with this. Remember the following, which is sort of hidden in my lecture. I keep saying that we need an MMSE denoiser, but actually we don't know how to design an MMSE denoiser. Unless it is a winner filter with L2 norm, we don't know how to design MMSE denoising. And in deep learning, for example, if you create a network, how can you claim that this is an MMSE denoiser? Because your loss, minimized L2 loss, it's not MMSE, it's just MMSE in spirit. So I think deep learning denoisers are performing better simply because they squeeze better performance and therefore getting closer. But by themselves, the architecture themselves are not proven to be right or wrong. And the main question still remains wide open. How do you design an architecture that can claim to be an MMSE of something?
Neat. Yeah, that's great. That's great.
There is one question from the audience, so from Christopher Alan Metzler. So I guess you can talk now. Go ahead and unmute yourself.
Cool. So yeah, so great talk. Thank you. So at the end, I was very interested to see, the STD, per pixel standard deviation estimates associated with the reconstructions, which seems, potentially very useful. To your knowledge, or so that's displaying the variance associated with the estimates, but not necessarily systemic bias in the reconstructions. Is that something you need to worry about, or it's not the same as the mean square error, I guess? And is that something you've given much thought to?
So what we show here are the first and the second moments of those samples. But it's very limited. The second moment is actually a matrix. What I'm showing you is the diagonal of this matrix. And no, we have not yet dived into the statistical properties of those estimates and what can be claimed about them. We do think that this approach will give us access somehow to talk about uncertainty in solution of inverse problems. For example, in medical imaging, that could be wonderful. Imagine that you get an MRI, and I will tell you on the region what differences can still accommodate your measurements and still be faithful to the data. Doing this is cumbersome. You're not supposed to sample many times and then show me the uncertainty. Could there be a direct way to get to the uncertainty? For example, some researchers like Ermon suggest that they can do it.
Thank you.
So but the bottom line to my answer is there is so much more to be done here to leverage the new forces that has been discovered in order to do something about uncertainty in these problems, uncertainty and statistical properties of those estimates.
Great. So
Cesar, can I butt in with one more question? Because I think maybe faculty should. There is a faculty meeting that's starting up, Mickey. But a lot of the folks here are students and postdocs. I just have one more quick question, Mickey, and that is, in this last stuff you talked about, is there an alternative to the SVD for to break this kind of cumbersomeness?
Not one that we see. We do see a way to speed up the SVD dramatically, but we don't see a way to go about. It's again the question of the relation between the Langevin noise and the measurements noise. And if you assume that they are independent, you get stuck. So they have to be somehow interconnected, and interconnection has to use the operators U and V from the SVD. Without them, you are getting stuck. But maybe there is a way around it. By the way, I have to add, earlier paper by Simoncelli and Ermon handled inverse problems without the SVD, but they assumed noiseless measurements. But it's not a valid assumption to assume that your measurements are totally noiseless. When noise exists, you are coming back to this pitfall of the necessity for the SVD.
Thanks. That's great.
Yeah, there is another question from the audience, so I'm going to. So Tan, you can ask your question and unmute yourself.
Okay, thank you. Very interesting. Thank you very much. I'm curious about full motion video, and is there a way that you can do denoise before you do temporal compression from live frame to frame, or is there strategies of doing so? Thank you.
The whole thing of treating video is not yet done and extremely challenging, but I would say promising. You know what? I'm sure we will be touching on it. We ourselves in my group developed neural networks denoising of video. So you might think that just take your video denoiser and plug it into this scheme, and you're likely to generate videos from nothing. It will be interesting to try. Nobody tried. So your question is terrific. Now, can you do it in order to leverage all sorts of additions to denoising? Good question. I don't know.
Great. So maybe I can use my superpower and finish with one question on my own, which is a question about the scalability. So how does this scale when you're thinking about larger images or maybe signals that are not 2D but 3D things. How does scalability plays a role in these approaches?
Well, most of the results I've shown you today are small images. And there is a reason for that. It's not only the runtime. Smaller images are treated better by denoisers, and therefore your MMSE assumption is getting becoming more correct to some point. So it's a challenge to grow to larger images, but people have done it already. For example, the other paper I mentioned that synthesized images and bit GANs is actually synthesizing large images. But you will always have to pay in runtime, because if your denoiser has to process bigger volumes, then it means that your whole algorithm is slower. There is a lot to be done here in terms of speeding up those algorithms, creating a bridge between diffusion methods and GANs, and better designing of denoisers. And all of these will converge to better synthesis, better solution of those problems. And we are trying to figure out what else can we do with denoisers, not just in those problems, but maybe compression. Why not compress images better?
Seems like we could follow the machine learning trend, and there will be a paper called like "Denoiser is all you need."
Maybe, yes.
Great. Yeah, it seems I don't see any additional hands raised at this moment.
Let me just add that the slides are already in my webpage. So anyone who wants to look at them and download them and use them, you're more than welcome. And of course, there will be the recording.
Yeah, this is great. I think this was an amazing way to start our distinguished seminars this semester. We had huge attendance, and I'm sure once the video gets posted on the YouTube page, it'll get a lot of hits.
Great. Thank you very much. Thank you for attending.
Oh,
Yeah,
thanks, Mickey. Fantastic. So, as always, but fantastic.
Thank you.
Thanks so much.
Thank you.
Bye,
So
guys.
I'll stop recording now.
Thank you. Have a good evening.